How is everybody doing so far? First day at our things open.
Good.
So Larry already introduced me. I'm Joydeep. I'm the director of IoT at Bridgera. We are headquartered here in Raleigh, North Carolina. We develop software solutions for IoT use cases. In fact, we have a IoT platform that we built that we use as the backend for the IoT software solutions that we develop. Today we'll be talking about talk to your things. So things means devices in case of IoT. So I'll be talking more about how you can communicate back and forth effectively between a device and the IoT cloud platform. So before I jump into the details of how we do the communication, I'll be talking a little bit about the end-to-end IoT solution. I'll be just setting the stage here. So any IoT solution starts with a device or a thing. Some of the devices are IP enabled, that means they can directly communicate over the internet to a IoT cloud platform. Some of the devices are not IP enabled, so like a Bluetooth device or a Zigbee device where you need a gateway or a hub in between for the devices to get communicating with the internet, and then eventually they will communicating with the IoT cloud platform. Then of course you have a communication channel between the device and the cloud platform, that is internet or cellular data, whatever you call it. And in the cloud platform, you have data ingestion, data processing, data storage, these type of capabilities. At the other end of the IoT solution, we have IoT apps. Those are custom-built IoT applications. Generally, and they can be a mobile app or a desktop app or a web app. Generally, people use those IoT apps to communicate with the device. But as you can see here from this diagram, generally the apps do not directly communicate with the devices, rather they communicate via the IoT cloud platform. So now let's talk more about the device to platform communication, how the different types of devices using different RF technologies they communicate with the platform. So let's start with the long distance IoT solutions. The most popular one is the cellular network. Any device which gets connected to the cellular network that becomes mobile, any IoT device. There are plenty of different cellular technologies exist out there. I'll not talk about 2G anymore, it's almost obsolete. But 3G, 4G, or different varieties of LTE. Irrespective of the communication or irrespective of the network that we use, every IoT device which use the cellular data, they have a SIM card inside it, and then they get connected to the cellular data and then communicate with the IoT cloud platform via the cellular data. Similarly, Sigfox, LoRaWAN, there are other long distance IoT solutions. I'm not going into the detail here, but as you can see that the devices, those are using the Sigfox or LoRaWAN network, they use some type of gateways or other network servers to hop into the internet and then eventually get connected to the IoT cloud platform. On the medium distance IoT solutions, I'll be talking about Wi-Fi, Zigbee, Z-Wave, and Thread, most four popular medium distance IoT solutions. Everybody knows what Wi-Fi is. Any device with a Wi-Fi chip in it can communicate via Wi-Fi through a Wi-Fi router to the internet. Zigbee is another type of medium wave solution which is used a lot in the home automation space, where there are multiple types of devices in a Zigbee topology. The end nodes or the end devices are the actual Zigbee devices. But apart from that, you can also have the routers and the coordinators. Eventually, the coordinators get connected to the internet. That's how, and they use different network topology like a mesh or star network topology. That's how the Zigbee or Z-Wave or Thread devices get connected to the internet using some other hubs in between. For the short-range IoT solutions, the most popular ones are Bluetooth, RFID, NFC. For Bluetooth, you need a phone app or a Bluetooth hub to communicate with the internet. For RFID, generally the RFID tags communicate with a RFID reader and then the RFID reader gets connected to the internet. That's how the RFID data gets transmitted to the internet. For NFC, the most widely used applications are the payment terminals. Nowadays, if you go anywhere, you'll see the Apple Pay or Android Pay over there. So NFC devices, when they come close to another device, they transfer the data using near-field communication. So here, as you can see, for this payment app, when the smartphone comes near to the payment terminal, the credit card data get transferred, and that's how they get connected to the internet and push the data into the cloud. So that's enough about how different types of devices using different radio frequency get connected to the internet. Now let's actually jump into the different IoT protocols. In the topic itself, I mentioned that be prepared to use different languages. Those languages are nothing but different IoT protocols. Before I jump into different IoT protocols, I'll be talking a little bit about the different challenges that we see in case of IoT communication. If you understand that, then you will appreciate more why those protocols exist and what type of problem these protocols actually trying to solve. Scalability. It's a huge concern for any IoT solution. Even though the amount of data transfer per data packet is very small, but if you multiply it with the number of devices in your network, and again multiply it with the number of times that the device communicates with the server, the actual amount of data transfer is huge. So scalability is a huge concern, and we need to make sure that any IoT protocol or any communication channel that we are using can support a huge amount of data transfer, huge amount of high-speed data transfer actually. Machine-to-machine communication. IoT is all about machine-to-machine communication. The Internet Protocol, HTTP, was designed for human-to-machine communication. It was not specifically designed for machine-to-machine communication. Also, HTTP was designed for a bigger amount of document-type data transfer, if you are familiar with. But in IoT, the nature of data is different. That's why the IoT protocols exist out there, which specifically address this concern, the machine-to-machine communication. Next point is event-based communication. The Internet Protocol, HTTP, doesn't understand event quite well, and it's a stateless protocol. For IoT, the event-based communication and event-based notification is very important. I mean, just think of a use case like if you have a temperature sensor and if you want to trigger your fan on when the temperature goes beyond 80 degrees Fahrenheit, then that's actually an event that is coming out of the IoT system. So you need to make sure that whatever the IoT communication protocol you are using, they have inbuilt support for that event-based communication. That's very important for any IoT communication. Then the next point, you really don't have much control about where the devices will be deployed. Many times the IoT devices, the cheap devices will be deployed in an unreliable, constrained network situation. And you need to make sure that IoT protocol, whatever you are going to use, has some support, inbuilt support, to make the communication reliable, even in that constrained, unreliable network. Mechanism to know the current state of endpoints. So I'll give you an example. So if you have 1,000 devices in your IoT solution, and you are constantly communicating with the devices, and you send a message to a device, you send a request, you are actually expecting a response back from the device. But if that device is offline that time, you are not going to get any response, right? But if you don't know the current state of the device, then there is a problem, because you will expect something back from somebody, but you are not going to get that. That's why that IoT protocol should support this thing, where you need to, or where you should easily get the current state of the endpoints of the devices. And security, I mean, I need an entire session to discuss about IoT security. I'm pretty sure that there are a lot of other sessions about security, but one thing I just want to emphasize here, that in IoT, the security is very, very important, and it is much more important than what it is in the web world. The reason behind that is, in web world, you can use the state-of-the-art security mechanism. You can implement that in the high-end servers. In case of IoT, you are actually dealing with pretty cheap devices. And most of the time, those pretty cheap devices, they don't have enough computing power to support those state-of-the-art security mechanisms. So, and in an IoT end-to-end solution, it is as secure as the weakest link. And most of the time, the device is the weakest link, right? So, irrespective of that, I'm not going into the detail of IoT security. What I'm trying to address here, that the communication between the device and the platform, that needs to be secure. Now let's talk about the actual IoT protocols. So the first one that I'll talk about is MQTT, Message Queue Transport Telemetry. This is the most popular IoT protocols now. It was invented by IBM. It's a publish-subscribe based protocol, and it uses TCP as the underlying protocol. In the center of MQTT, you have an MQTT broker, and all other devices or all other players in MQTT ecosystem are clients. That means all the devices are also clients. At the same time, the IoT cloud platform itself is a client. Any client can publish topics, public messages via some topics to the MQTT broker, and also the other clients can subscribe to those messages. Depending on which message or which topic you subscribe to, that message will be delivered by MQTT broker. Broker actually controls the routing. The MQTT is an extremely lightweight protocol. The underlying protocol is TCP, I already talked about it. For better security, you can always use SSL or TLS, but you have to understand that SSL or TLS are not the lightest of the protocols, and it adds significant overhead to the communication. So if your IoT solution can support it, yes, go for it. If it cannot support, then you can use your own custom encryption algorithm. MQTT doesn't have an inbuilt one, but you can add your own custom encryption algorithm to make it more secure. Also, MQTT supports varied level of QoS, so that quality of service. That's the MQTT's way of adding reliability in the communication. I talked about that communication in the constrained network for the devices. So there are 3 levels of QoS available for MQTT communication. At most one, which is the least reliable, it's basically just fire and forget, whatever is being supported by TCP, nothing more than that. At least once, it's somehow reliable. That means, yes, the message that you are delivering will be received by the recipient, but there is no guarantee that the message will be received just once. It can be received even multiple times. So that means at the end, at the recipient end, you need to make sure that you have a filtering mechanism to filter out the duplicate messages. And exactly once is the most reliable one, where it is guaranteed that whatever message you are sending from the client will be received by the recipient exactly once. And I added a flowchart diagram here as well to describe that. I'm not going into the detail, but you can definitely take a picture and explore it later. We talked about knowing the current state of the device in case of IoT. And that's MQTT's way of doing it, last will of testament, LWT. So can everybody see those attributes here? It's pretty small. I don't know if anybody can see it, but if you...
It's clear.
Clear? Oh, okay, very good. Yeah, so when you... Yeah, I just mentioned a MQTT connection packet, how it looks like and different attributes. So you'll probably, so the interesting thing here for last will and testament are, there is a last will topic here, if you can see my cursor, and there is a keep alive setting, which is set for 60 seconds here. So basically, when you connect, when the client connect to the broker, that keep alive setting tells the client or the broker, if I don't hear back from this client in that keep alive time, that is in the last 60 seconds, I will think that the client got disconnected ungracefully. That's what it is all about. If the client got disconnected ungracefully, if the broker thinks that, then the broker will send a message that is the last will message. Here I mentioned it as unexpected exit. And there is a last will topic as well. So all the clients or subscriber, whoever subscribed to that topic, they will get that. So if I'm interested to know the current state of a particular device, I'll be subscribing to this topic, last will topic. And whenever the broker will decide, hey, I'm not getting any kind of communication from this particular client, it will send me that message. That way I know that yes, that particular node is currently disconnected or offline, and I will change my logic accordingly. On the implementation side, and I mentioned earlier in my topic that I'll be talking about the open source implementation. I gave a GitHub link. You can always go there and download the different MQTT client libraries if you want to play with it. There are Android and iOS libraries available out there, which you can download in your smartphone and make your smartphone as an MQTT client and start publishing messages. If you are doing some POC kind of stuff using Arduino, there's an Arduino library out there, download it, play with it. If you are doing some serious stuff, there is Java or Microsoft.NET clients also available out there. And on the broker side, there are open source brokers available out there. Also, there are enterprise grade support available for some of the brokers. So we use Mosquito. You can use HiveMQ, EMQ, CloudMQ, VarmMQ, any other broker. QAP. So that's another protocol that is gaining popularity nowadays. It's Constrained Application Protocol. It's specifically designed for, or it has a good support for the devices which runs in the constrained network. It's more like HTTP or RESTful protocol, and it also has the methods, the HTTP methods like get, put, post, delete, support for those methods. The underlying protocol for QAP is UDP, which is pretty unreliable. So a basic reliability scheme is built on top of it to support the reliability for the QAP kind of communication. And also to make it more secure, you can always use DTLS, that is Datagram Transport Layer Security. MQTT support IPv4, IPv6, low PAN, and it supports unicast and multicast. And people who are familiar with IPv6, they know that IPv6 also supports multicast. For QAP, unicast is used for request response type of messages, and multicast is used for server discovery, resource discovery. Actually, QAP supports the server discovery as well. On the implementation side, I'll be just mentioning a few. So as I mentioned that QAP is widely used for the devices which runs in the constrained unreliable network, and I have a link here where you can download all the different supported libraries. So Contiki is an operating system that people use widely for devices that they build to run in a constrained network, and RVM is a QAP client, ER here, as you can mention, that people use for the devices which runs on Contiki. Also on the browser side and the smartphone side, there are clients available for iOS and Android. There is a Firefox plugin available out there, Copper, CU. If you really want to you are interested in playing with QAP and just want to see how it works, you can have that Firefox plugin installed and you can play with it. TCP. Of course, it's the oldest of the protocols. Was not specifically designed for IoT, but there are plenty of devices still out there which uses TCP, and that's why I think that it's worth mentioning here. In case if a device is communicating to the platform via TCP, if you want to communicate back and forth with the devices, you need to have a TCP listener service running in your server. And that listener service has to open up a TCP port. When a device wants to communicate with your platform, the device will have to open up another TCP port, and they will have to do a TCP handshake, and that way the communication will be made. That's how the data will be transferred. So that's the one-way communication, when the device is communicating with your platform. Now if you want to do a two-way communication, device to platform and platform to device, so here is the catch. Most of the time when your devices are using IPv4, the IP address will be dynamic, because there are not enough IPv4 IP addresses exist out there. If it is IPv6, it's different, and probably you'll get a static IP. So if you really want to do a communication back from the platform to the device, you actually have to request for static IP from your network provider or cellular network provider. Otherwise, without knowing the particular IP address, you will not be able to communicate the TCP communication. SMS-based communication. So why it is important? It's still important today. Because in IoT, people want to save battery. And the way to save the battery is to put the devices in sleep mode. And once the devices are in sleep mode, the only way to wake it up, the easiest way to wake it up is to send a SMS text message to the device. Once the device will get the SMS text, it will wake up and it will start communicating. That's why the SMS-based communication is still out there and it's important. For SMS-based communication, people generally don't use the commercially available SMS sending platform. There are some unreliability in it because the characters that we send for IoT communication, many a times the cellular network thinks those are garbage and they will put the messages into spam and they will never get it. So the best way to achieve the good communication, SMS-based communication, is to use SMTP protocol, short messaging peer-to-peer protocol. In SMTP, you have to run a client, which is ESME, external short message entity, which will be running in your cloud platform. That ESME will start communicating with a gateway called SMSC, Short Messaging Service Center. And via that gateway, it will send the SMS text message to all the devices. You can also get use the SMS communication to get the response back from the device. For that, you need to get a shortcode from your telecom carrier. If you get a shortcode from a telecom carrier and put that in your platform, and then program the device to send the messages or send the response back to that shortcode, then the devices can send. So that's the way you can actually implement SMS-based two-way communication, back and forth communication with your device and platform. For that, from the implementation side, there is a open source library available out there called OpenSMTP. We use it. You can also download free and implement it. There are a few important methods that you need to implement in your code. Those are like abstract methods you need to override it. Like bind, enquire, link, submit, SM, and unbind. Those are the four most important. If you're interested, we can talk about it later. Well, I'm pretty much done with most of the protocols. There are other protocols also like UDP, XMPP, AMQP. They're not that popular, not used widely, so I'm not going to discuss it here. I'm just going to skip it. You can take a note of it. Okay, so we talked about the back and forth data communication between the device and the platform, and different languages, means different protocols that you can use to communicate back and forth. Now, once the data reaches your platform, then the platform will be ingesting the data, it will process the data, and it will store the data. And also it will have the support for different IoT applications, IoT apps. So before I'll jump into the detail of that, I'll be just talking a little bit about why we use big data technologies in case of IoT data management or data processing. Because on the server side, in the cloud side, we use big data technologies. So I'll be explaining that with the three attributes of big data: volume, velocity, and variety. And all three applies for IoT. We talked about the volume of data that we need to handle, the huge volume of data. It's not even terabyte, it's petabyte, sometimes zettabyte for different IoT solutions. And traditional servers or traditional technologies cannot really easily handle that kind of big volume of data. Also, the data in motion, the data that is coming to the IoT platform, comes at very high speed because there are plenty of devices in case of IoT, the devices generally stream the data. So if you multiply with the number of devices and number of times it sends the data, actually the data comes in the IoT platform at very fast rate. So that's the velocity part of big data. And variety. Every device has a different data structure. And also, if you think of it, even for the same device, the data structure evolves from different firmware versions. So the data structure can be something with firmware version 1 and it can be completely changed for firmware version 5. So if you are supporting those enough number of devices, different types of devices, you need to have a support for storing semi-structured and unstructured data in your database. And the traditional technology stack are really not, RDBMSs are really not designed for that. You cannot really change your data schema on the fly quickly. So that's why we go for big data technologies. There are other reasons as well, like in the big data technology stack, the things like fault tolerance or scalability is built in. So if you are using big data technology stack, you are getting support for the fault tolerance, things like fault tolerance and scalability, which are pretty important for IoT. You really don't have to write a lot of custom code for that. So that's a good thing. So on the data ingestion side for the platform, we talked about all the different protocols. So if your platform is going to support a wide variety of devices, we need to make sure that the platform, the data ingestion layer, has support for all these different protocols. At the same time, the platform should support the SSL or TLS type of data encryption algorithm. Because if you don't support that, and if your device is supporting the device that you are communicating with, you supports that SSL or TLS type encryption, then you will not be able to support it. That's why the SSL and TLS type data encryption algorithm support should be there. It should be scalable. We talked about that. It should be fault tolerant because we are using big data technologies. That's why it will be fault tolerant. And also the data ingestion layer should be very lightweight. It should not have a lot of data processing logic in it. It should just do some data cleaning or data filtering type of easy work and push the data back to the processing layer for the further processing. On the implementation side, we use Apache NiFi, another open source tool, to build data ingestion layer. Apache NiFi is a distributed data flow engine. There is a stripped down version of Apache NiFi called MyNiFi. If you are building IoT hubs or the gateways, you can always run MyNiFi in it because NiFi is an enterprise grade thing. You need a big server to run it. So for the smaller hubs and stuff, you can use MyNiFi. HDF is Hortonworks data flow. It's essentially Apache NiFi, nothing different. But if you are looking for enterprise grade support, then you should go for HDF because then you will get the enterprise grade support from Hortonworks. On the data processing side, we do two types of processing, real-time data processing and batch processing. So the real-time data processing is on the data streams, that what we get from the IoT devices. We use Apache Kafka and Apache Storm, both open source for real-time data processing. You can also use RabbitMQ and Apache Flink for real-time data processing. For batch processing, we generally don't do it on the, you cannot really do it on the streams. For batch processing, it's more like offline data processing. So the data needs to be stored in a database, and then offline over the night or sometimes you need to do the batch processing. And most of the time, the batch processing is being done for some analytics type of use cases or for getting some business intelligence out of the data that you are capturing from the IoT devices. And for that, we use another open source tool called Apache Spark. On the IoT data storage side, we talked about the different attributes of IoT data. It's large volume. It has a different variety because the different devices stream different types of data. So because of that large volume and different variety of data, we did not use the traditional RDBMS data storage to store IoT device data. Rather, we went for NoSQL database storage, where it can handle large volume of data sets. Also, it can store different varieties of data, different types of data structure. We use MongoDB, another open source database. You can always get an enterprise grade support from MongoDB, but it is open source. You can always download and start using it. As our NoSQL database, which is a document type database. We can also use Cassandra, a key value type and NoSQL database. Good thing about NoSQL database is most of these NoSQL databases has a support for something called sharding or horizontal scaling. So because of that huge amount of data, if you think of it, if you put that huge amount of data is just one storage or one server, if you run a complex query, it will take really long time to get an output. Instead of that, if you do the horizontal partitioning of the data and put that into multiple cluster, when you run a complex query, the output will be coming much faster. And those are already inbuilt into the NoSQL databases. If you have to achieve the same thing with traditional RDBMSs, it's a lot of work, and most of the time it will not be able to do that. So NoSQL databases are really good to store the device data, but it's not good for the data which needs transaction support, which needs the ACID properties. So for this type of data, we still use RDBMSs. So we actually use a mix of NoSQL and RDBMSs. So the data like the customer data or financial transaction type data. I mean, in an IoT use cases, apart from the device data, you also have other data. So you need to, so for those type of data where there is those type of relational data, we still use the RDBMS storage. MySQL is an open source RDBMS. We use it all the time. Postgre is another open source. Otherwise, you can always use Microsoft SQL Server, Oracle. They are not open source, but they are great databases. Okay, so we talked a lot about all these different communication mechanisms, how we communicate between back and forth between the device and the platform. Once the data comes into the platform, then how we process it, how we store it. Now, in reality, how it happens. So I'll be explaining that with a use case, a fleet tracking use case, and the thing that I'm explaining here is creating a geofence. So as you can see on the left-hand side, I have an IoT app, which is a web app. And on the right-hand side, I have the device. So this is a fleet tracking use case, so the device is inside the truck, and it is a OBD2 type of device, which is plugged inside the truck here. We are using MQTT mechanism to publish subscribe messages between the clients. So this is this use case is to create the geofence. First, the user will use the IoT app to send a request to the IoT platform and tell that, hey, create a geofence for me. The platform gets the request. It will publish a command to the MQTT broker to create a geofence. The command will be sent to the actual device because the device has already been subscribed to that type of messages. So in reality, that this is the MQTT topic that the platform published the message to. And we already talked about that publish subscribe mechanism in MQTT, if you remember, just a few minutes back. And the topic is request / the device ID, which is the IMEI here, / geofence. The device here, this is the device unique ID, that IMEI. The device subscribed to any messages or any topic starts with request / that particular IMEI. So anything that you send with that request / that particular IMEI and then tell anything, that will be reaching to that device. So even though you have 10,000 devices in your solution, you can specifically send the command to that particular device using MQTT. Now this is the actual message that you are sending. This is the body of the message. That was the topic, and this is the body of the message. And the body of the message, as you can see here, I'm telling that this is the latitude and longitude. That means the center of the geofence, and the radius is 300 meters. The device got it, it created a geofence. Now the next one that I'll be telling is getting the response back from the device to the app and sending it to the customer. So here, the use case is the device entered into the geofence. As soon as the device entered into the geofence, it emits a signal back to the broker, and then it will be sending back to the client. The truck entered into the geofence, the device center published an alert. The alert was received by the platform. And here is the topic. The topic is event/geofence. The platform is subscribing to any topic which starts with events. So anything that you published with event/ will be reaching to the platform, and platform will get that. But how the platform will know who sent the message? If you look at the message, the actual body of the message, there is an IMEI here, which is the unique ID of the device. So from the body of the message, the platform will know, hey, I got this message which is about a geofence alert, and it was sent by this device here. And it also has a message that the geofence 1 was, the device entered into the geofence 1, the current latitude, longitude of the device, the GPS accuracy, all these stuff, whatever the device wants to send. When the cloud platform gets that, it processes it, it knows that this is an alert that I need to send back to the application, it sent an alert to the application, or it sends an alert to the user mobile device using SMS or push notification. Okay. So that's the end of my session, and I'll be taking a few questions here. But before that, here is a link for our IoT ebook. Basically, we published a free ebook. It is a joint collaboration between Bridgera and Riot, and I will suggest you guys to go into this link, bridgera.com/ebook, and download this ebook. I mean, if you are really interested in all these things I talked about, you will know more. Also, I didn't have any live demo with me today, but we have a booth here just in front of the 305, room number 305A. So if you guys are interested, you can always stop by. I'll be there, my team will be there, and we'll be happy to show you how all these things actually work in real life. Thank you. Any question, anybody?
So there was a publish, right? Create geofence was a more of publishing. And so how did, I mean, I didn't see how the truck got subscribed to that publish.
So in the beginning, when you deploy the device, that time itself, you have to program the device to subscribe for different topics. So if that device is subscribing for topics which are like this request that basically what happens is, in this case, the device will not subscribe to a particular topic. Rather, they will use wildcards. If you are familiar with wildcards, so the device will be subscribing to any topic which starts with request / its own IMEI or if. Okay. So anything that I'll be sending from platform using that IMEI will be always sent to that device, and it is at the time of device provisioning that will be, and of course that will not show. Okay. Thank you, everyone.
Thanks.